Okay, Muskan, let's continue from where we left yesterday. So today we'll be
Okay.
learning about classification based on molecular forces regarding polymers. Okay. So
Yeah.
as we already know, a large number of polymer applications in different fields, okay, depending on their unique mechanical properties like, tensile strength or elasticity or toughness can be classified. Okay.
Yeah.
Now, when I say mechanical properties, these mechanical properties should be governed by certain forces. So, what kind of forces are these? These are actually intermolecular forces, like it might be hydrogen bonds, it might be van der Waals forces, which is actually present in that polymer. Okay, and
Okay.
because of these forces present in those polymers, okay, they bind the polymer chains, and then we get a required property kind of a polymer here. Understood?
Yeah.
So, like if I talk about the very first one, we can call this as elastomers.
Okay. So that's one of the the intermolecular forces that are used.
Yeah, this is one of the polymers.
Oh, okay.
Elastomer is one kind of a polymer. So, what exactly is an elastomer? Uh, the word elast or elasto clearly indicates that it is something which is stretchable, right? As we use the word elasticity or elastic, right? So, it's a
Yeah.
property of something being stretched. So, what exactly are elastomers? They are rubber like solids with elastic properties in it. Okay. So, in this kind of elastomeric polymers, what exactly happens is the polymeric chain or the polymer chain are held by intermolecular forces, but they're not very strong. They're very, very weak intermolecular forces. That is the reason one can actually stretch these polymers, isn't it?
Yeah.
If the intermolecular forces would have been very strong, there would be no chance that this could be stretchable. Okay. So, because of the presence of these weak binding forces, it allows these polymers to be stretched. Okay.
Yeah.
So, I spoke about crosslinks yesterday. So, a few
Mhm.
crosslinks, yes, a few crosslinks actually introduced in this kind of chains, which actually helps the polymer to retract to its original position. Now, when I say retract, for example, if I'm using a rubber band, okay, and if I stretch the rubber band and I can release my fingers, so what happens? The rubber band actually comes back to its original position.
Yes.
So that is called retracting. So because of the few crosslinks which are present in it, that actually allows the material or that polymer to retract or to come back to its original position. Okay.
Okay.
Even when you release the force, as long as you're stretching it, it remains stretched. But the moment you release the forces, it goes back to its original position. Okay. So
Okay.
neoprene is one such example. You have Buna S, Buna N. These are some of the other examples for this. So neoprene is one example. Then you have Buna S, you have Buna N as well. So these are some of the examples for elastomers. So I think you have understood what elastomers are. Okay.
Yes.
And if we actually draw its structure, so it's something like this CH2, C, double bond H, then CH2. Now this is one unit of that elastomer. Okay. We also have a chlorine here. Now if I put an N, which means if you use many such units, then that gives rise to an elastomer, a chain of
So the N would be like how many there
a
are of
large,
those
a
compounds?
large, exactly. It actually indicates a large number. Okay.
Oh, okay.
So
So
the
can you
first,
substitute the N for a number?
yes, absolutely, it could be substituted. Okay. So
Okay.
after elastomer, the next polymer that we'll be learning is about fibers. Okay. So where exactly are these fibers used? Now, fibers are generally threads forming solids. Now, these threads actually possess high tensile strength and high modulus as well. So that's the reason you can't stretch fibers, right? So
Wait, what
the
are fibers?
fibers are threads used to make
Oh
a
no, you
cloth.
can't.
Okay, so it has a high tensile strength. At the same time,
So the intermolecular forces would be stronger in the cross links.
exactly. No, there need not be. There has to be a crosslink in it. But even though the forces present in them, they are very strong. Okay, and
Okay.
the reason why the forces are very strong is because of the close packing of the chains. Understood? That's one of the basic
Right.
reasons here. Okay. So, as you said, it's correct. Like the characteristic of a fiber can be attributed to the strong intermolecular forces. Like what kind of forces actually can be seen in this? When I say strong, it is basically hydrogen bonding. Okay, so
So the hydrogen, wait, in intermolecular forces or whatever forces there are, is it
yeah,
always just like hydrogen bonding?
yes, here right now in this case, it's because of the
Yep.
presence of the hydrogen bonds. Okay, these are quite what you say, strong in nature. Okay,
Okay.
so because of these strong forces present in this, it also leads to close packing of chains because whenever the forces are high, you actually can see that these polymer chains will be very closely packed to each other. Okay,
Okay.
due to which it also can give you a crystalline nature.
Yeah.
Okay, so that's another thing. Understood? And examples are many, like you have nylon, for example. Okay, then we have polyester. This is another example for a fiber which is formed from a polymer. Okay,
Okay.
and polyamides. So elastomers is one, fibers. So now you understood the basic difference between what an elastomer is, what a fiber is, and why is the difference basically between the two. Okay.
Is it just those two types or is there more?
Oh, there are more. There are more. You need to know that
Oh,
actually. Yes. So the third one is thermoplastic polymers. Okay. So generally you have your polyvinyls, for example, or your polythenes.
yes.
Yes. So when we talk about thermoplastic polymers, so one second, let me name it. Thermoplastic polymers. Okay. So what exactly are thermoplastic polymers? They are linear or slightly branched long chain molecules. Okay, in nature, and they are capable of repeatedly softening on heating. I gave you an
Yes.
example yesterday, like bakelite, for example, cannot be softened on heating. It's a different kind of a polymer. But when you talk about thermoplastic polymers, it can be softened on heating, and again, once it cools down, it actually hardens.
Yeah.
So what
So
exactly
when it's
happens here
soft, then you
is
can reshape.
yes. So here this kind of a polymer will actually possess an intermolecular force, which is something between an elastomer and a fiber. You got that?
Oh,
First, what we
okay.
spoke about elastomers, which can be stretchable. Fibers they have got high tensile strength; they can't be stretched. So when I speak about
Mm-hmm.
thermoplastic polymers, it will actually comprise of forces which are in between those elastomers and fibers. Okay.
Okay.
So
So it's
here,
in the middle.
yes. So here the intermolecular forces are between these two. So that we can mention here. Intermolecular forces between elastomer and fiber can be seen in this. Okay. So what could be the examples of such kind of thermoplastic polymers? So examples could be polythene. Okay. Then you have PVC, polyvinyls, and then also polystyrene. So this is the third kind of a polymer. The fourth one would be thermosetting polymers. This is just exactly opposite to that of thermoplastic polymers. So what exactly happens in thermosetting polymers? So here what you can see is cross-linked or heavily branched molecules, okay,
Yeah.
and of hydrocarbons. And when you heat them, they undergo extensive cross-linking. Now this cross-linking will actually form in molds, and they again become infusible. When I mention the word infusible, once you heat them and they take a shape, okay, whichever they are cast into a mold, you cannot soften them after that. So basically, these kind of polymers cannot be reused. Okay, you can't use them again. Okay, and they are also infusible, so you can't soften them on heating, and that is the reason you actually find the use of thermosetting polymers in the form of bakelite, which is extensively used in electrical switches. Okay, it can also form urea formaldehyde resin. Formaldehyde resin. Okay,
Yeah.
so these are the basic, four kinds of polymers. Okay, which depending on the intermolecular forces can be classified. Okay, so and next one, what we're going to learn is about classification based on growth polymerization. When I say growth, it actually includes addition and condensation polymers. Okay,
Yeah.
yes. So nowadays it is referred to as chain growth polymers and step growth polymers, depending on the type of polymerization mechanism that they undergo during their formation. Okay,
Okay.
so it's basically that. So in this, what happens is, as I said, one is the addition or chain growth polymerization. The second one is a condensation or step growth polymerization. Okay, and here also, when we say these two, so the mode of polymerization leading to an increase in the length of the chain or growth of the chain can take place through the formation of either free radicals or ionic species.
Oh,
Okay.
okay.
So here you now basically have to learn about what is free radical mechanism which can allow this addition to take place. Okay.
Yeah.
So if we speak about the free radical
So
mechanism,
that's one of the classifications of uh growth
one is
for
free
plastic.
radical mechanism. Okay.
Yeah.
And second one is preparation of some important addition polymers. That's the second one, which again will include low density polythene in that, high density polythene. Then we have Teflon, which is polytetrafluorethene. Then we have
Mm-hmm.
polyacrylonitrile, okay, which
Yeah.
has, yeah, okay. So these actually will be included in that. So first, let us understand what is free radical mechanism. So a variety of alkenes or dienes and the derivatives are polymerized in the presence of a free radical generating initiator. Now, what is this actually? The entire process will take place in the presence of a catalyst. Okay,
Okay.
like this catalyst can be something like benzoyl peroxide, acetyl peroxide, or tetrabutyl peroxide. So, in the presence of these kind of reactions will be initiated. Okay, so let's suppose if I'm taking what is a polymerization of ethene is
Yeah.
changed to polythene. So this has to consist of heating or exposing to light. Okay, so how
Yeah.
can I convert this polymerization of ethene to polythene? Small amount of heat, okay, or exposing to light a mixture of ethene with a small amount of benzoyl peroxide initiator. So when this
Yeah.
happens, it then takes the form of a polythene. Understood? So here we are using certain kind of radicals, okay, to initiate this step, which can also be called as the chain initiating step. Okay. So to begin, we use what to say polymerization of ethene, which is exposed to light, along with a small amount of a catalyst, which can be benzoyl peroxide. Now,
Okay.
as this radical keeps reacting with another molecule of ethene, because I'm not just using one ethene molecule, there will be several. Okay. So as I keep using this, another big sized radical will be formed, because if I add two units, it's going to give me a larger unit. Now these two units, if it again combines with the third one, it becomes much more larger. Okay.
Okay.
So this repetition of the sequence with new and bigger radicals will be carrying the reaction forward. So when I
Yeah.
started off, I'm going to call it as a chain initiating step. But at some point, I even need to like try to understand. When I started off, I'm going to call it as chain initiating step. When this process is going on, we'll call it as chain propagating step. And at some stage, I also have to stop this. Okay, to get a final product. So when I stop, then I'll name it as the chain terminating step. Okay.
Oh,
So try to
okay.
understand. Chain initiating is to begin. Then I have chain propagating, which is actually carrying the reaction ahead. And then of course I have the chain terminating step as well. So first step is chain initiating step. Then I have chain.
And chain propagating comes in the middle.
Yes,
So
it
is
is a
that like when
process
it's like halfway?
halfway or midway. Yes, and then
Okay.
when we need to stop this, then you'll have the chain terminating step, because if you do not stop, then the chain keeps going on longer and longer.
Yeah.
Okay. These are actually steps which are included in free radical mechanism. Understood these? Now, the next will be preparation of some important addition polymers. How can you prepare them? For example, if I talk about polythene, okay. Now,
Is
even in
it preparation
polythene,
of additional
yes,
polymers?
yes,
Yeah.
preparation of
Okay.
addition polymers. So, in that,
Hmm.
the first of its kind would be polythene. Now, even in polythene, I've got two types. One is a low density polythene, and the other is a high density polythene. Okay.
Yeah.
So, when we are talking about low density polythene, so one second, low density polythene.
Is polythene the only one that's in the preparation of
No, no, no.
addition
Apart from
polymers?
polythene, you also have Teflon.
Oh, okay. How many are there in that one? Is there more than
You have
free
three
radical?
basically. I mean,
Oh,
basically,
okay.
we'll be having three. One is polythene, the other is Teflon, and the third one is polyacrylonitrile. Okay, these are the three. I'll teach you about polythene first. So, when we talk about polythene, that was a low density one. So, this is obtained when ethene is put under high pressure. High pressure in the
Okay.
sense, if we actually subject it to atmospheric pressure of between 1000 to 2000, and that to at a temperature of 350 to 570 Kelvin scale. So atmospheric pressures will be somewhere between 1000 to 2000 atms, and the temperature would be somewhere around 350 K to 570 K when I require a low density polythene. Now, this also has to be done in the presence of a catalyst, like an initiator,
Okay.
a free radical mechanism. Yes. So here we're using some kind of a peroxide again, okay, which can be a catalyst, not can
So
be.
it can be any catalyst,
Yes, benzoyl or
but
even
people,
mostly they use benzoyl peroxide or any kind of a
yeah.
peroxide initiator. Okay,
Okay.
and this low density polythene through the same steps again. I we classified the steps initially. What steps were those? The chain
And
initiating
chain
step, the chain
initial,
propagating step, and then the chain terminating step.
chain terminating.
Yes, in the same way, this process actually goes on, and here that results in a very, very highly branched structure. But here, what
Okay.
happens is, here the low density polythene is basically, inert to any chemical substance. It
Yeah.
can react very easily. It's tough, but it can be flexible. Let's say you see the polythene covers, for example, or even your soft drink bottles that can be squeezed, isn't it? It's not hard like glass, okay?
Yes.
Or even toys or, flexible pipes. So these are all made out of this low density polythene, okay?
Mm-hmm.
So exactly on the other side, you have the high density polythene. This is also found when addition polymerization of ethene takes place, but in the presence of a hydrocarbon solvent. And here you have a very, very important catalyst which can be called as triethyl aluminium or titanium tetrachloride for a high density polythene. Okay, I'll just put it in short as HDP. And the catalyst that we are going to use here is triethyl aluminium, or the other one is titanium tetrachloride. These are the catalyst which will actually initiate these reactions to take place to form this polymer. Okay,
Yeah.
so here the temperature is between 333 K to 343 K. Temperatures are not much high, because of which we get this high density polythene. And even atmospheric pressure, like you saw, for obtaining a low density polythene, we had to subject that to an atmospheric pressure of 1000 to 2000. Here we are bringing down to literally 6 to 7 atmospheric pressures.
So is the 1000 to 2000 only for like low? Is that
Low
like
density,
very
yes.
low?
It's a
Okay.
very high atmospheric pressure, because of which what happens is the final product is not very, what do you say, does not have a very high density, because you're
Oh,
forcefully putting it under a huge amount of pressure. Here we are allowing it to, the process to take place at a normal pressure, because of which
yes.
you get a high density polythene here. So there are linear molecules, and because what is happening is you are not subjecting it to extreme conditions, because of which what happens, it can actually, carry on the entire process at its own speed. And here, basically, when you talk about high density polythene, what happens is the reason why it has a high density is due to the close packing, because of which
Okay.
we get a polythene which is chemically inert, does not really, get damaged when certain chemicals come into contact with these. They are more tough and hard.
Okay.
So yeah, so for example, buckets or dustbins, for example, they are quite hard in nature.
Yeah.
Okay, and even pipes, like pipes which are used for, what do you say, for laying those
So,
overhead tank lines. Hmm.
all
The
right.
water
Yeah.
from the overhead has to come to rooms through a pipeline. So there you can use these type of what is a high density polythene. Okay.
Okay.
So whenever try to understand something in general, also when you're subjecting something to a very extreme condition, you will not get the best out of it. Understand? So it will be like more delicate or more brittle, which can be easily broken. But when you're allowing it to, happen, the process to take place under its own speed, then what happens? The outcomes will be much more, stronger, harder, okay, more tough.
Okay.
Huh? Understood this?
Yeah.
Next, let us go through Teflon. So how exactly is Teflon manufactured? So here, to manufacture Teflon, you first need tetrafluoroethane. Okay, and along
Yeah.
with this, you also need a catalyst. Now here, the catalyst for manufacturing Teflon will be using a sulfate. Okay, so first of all, tetrafluoroethane plus the catalyst that we are going to use is the sulfate. Okay. This is what we are going to use. And here, this Teflon will be subjected to high pressure. and because of
So
which what
that's the
happened?
catalyst that gets used to make
Yes,
Teflon.
yes, that is
So only that
persulfate.
one.
Well, basically, mostly, okay.
Okay.
Or else you can even use a free radical, but generally persulfate is used. And once you get the manufactured product, finally, that is Teflon, it is basically chemically inert. Do you know where Teflon is used? We normally use
No,
a Teflon coating. It's used on
I
frying
don't even know.
pans. They use in frying pans. That's why they say it is
Oh,
non-stick. The oil doesn't stick to the pan is because of this Teflon coating.
oh, okay.
Yes, isn't it? You must have seen. Even
So
oil can float in that pan. If you must have seen
yeah,
a
it
Teflon
doesn't
coated
stay.
pan. Yes, it doesn't stick. That's why we said non-stick. Why are we saying non-stick? Because that particular base is actually being coated with Teflon.
So then that means it's, is it a very light liquid
Uh,
or
yeah, light,
solid?
but no liquid generally. It is in the form of a
Okay.
liquid which is actually spread on it. And
Yeah.
when it comes to this reaction with chemicals, it's chemically inert. Or else then what happens
Okay.
if you use, if it's not chemically inert, if any normal chemical also falls on it, it would just rip and come off. Okay.
Yeah.
At the same time, it is also resistant to attack by corrosive reagents, because of which you're making it or you're using it for making oil seals and gaskets. And at the same
So
time, it
this
can
gets
be,
reused.
yes. And also, we use it for non-stick surface coated utensils, like a frying pan. Nowadays, they even coat the vehicles with Teflon. Okay,
Oh,
so that yes, because the vehicle, a car or a bike, should not be subjected to its minor scratches on it. So to avoid that,
mm,
then they even have these vehicles coated with Teflon. So this is
yeah.
how the Teflon actually forms. The last one, of course, is polyacrylonitrile. This is the last one. Polyacrylonitrile. So what is this exactly? So here we are taking acrylonitrile basically.
So that's a
When
third
you have,
one.
yes, that is the base actually. When you have many units of acrylonitrile, it becomes polyacrylonitrile. And this also is actually being formed in the presence of a catalyst called a peroxide. Okay. So where is it used? Nowadays in the market, you get artificial wool.
Yes.
It is exactly this polyacrylonitrile. It gives you an exact texture of that of a wool. So
Yeah.
you can't even like differentiate which is the original wool that has been fleeced from a sheep, or which one is polyacrylonitrile, unless and until you have real good knowledge of finding with the textures. And because wool cannot be like if it I mean it's not affordable to everyone. That is natural wool because it is expensive. Anything natural is obviously expensive, I said, because we have that
Yes.
limited quantities. So this polyacrylonitrile can be used as a substitute for wool in making
Okay.
commercial fibers like what? Olon or acrylan. So these are two basic, you know, fibers that can be obtained from polyacrylonitrile.
Yeah.
So here, after this is of course addition reactions. Okay. In the next class, what we'll be seeing is condensation polymerization. Okay.
Wait, how do you know
So
if it's an addition reaction? Is it because there is a catalyst present and then you have to add it into it?
mhm,
Is that why it's an addition?
yes. And
Oh.
basically, in condensation, what happens here is that actually basically results in loss of some simple molecules. You'll be losing something in the end in those reactions. Either you'll be losing water at the end of the reaction or an alcohol. Okay, so
Mm-hmm.
that is a clear indication of how a condensation polymerization will look like. I'll also give you the formation of these substances. Okay, I'll just make a pic of that and then I'll post it to you how
Okay.
exactly that can look like. Okay, So have you
So
understood
this
this
one's,
part?
yeah. So they're also classified as addition reactions because there is addition to it, right? They don't remove anything, like they're
In
not
what?
losing anything.
In what? In condensation?
It, no, no,
No,
in
yes,
these
yes. No,
four.
no, yeah. In these four, there's no chance of losing anything. No.
So addition reactions.
Yes. In
Okay.
condensation, obviously, you'll be losing uh,
Yeah.
either water molecule or an alcohol. Okay. Depending
Okay.
on that.